General relativity, step by step. After a monumental amount of effort, we've finally stated the Einstein field equations. And now we can start to have some fun with them. And now we can start to think about astrophysical phenomena like black holes, which are wonderful things, and I'm going to spend 20 or maybe 30 screencasts talking about black holes. I haven't quite decided how to cut it up yet, but here we go. So I'm going to consider an object of mass m, and I'm just going to consider an isolated object of mass m, and it's spherically symmetric, and I'm just going to see what happens, and I'm going to apply the tenets and the principles of general relativity. But before I do that, I'm just going to do a bit of dimensional analysis. So what have we got at our disposal? We've got the mass m, which is in kilograms. We've got g, big G, which is Newton's gravitational constant. It's always worth writing out the fundamental equation, d squared, and so g equals a force, which is kilograms meters per second squared, that's the force, times d squared, which has gone up to the top, over kilograms squared. So what have we got left? We've got meters cubed per second squared, kilograms squared. Meters cubed over second squared kilogram. Was it kilograms squared? No, it's not kilograms squared. I think there's only 1 kilogram left on the bottom. There we go. And of course, we've got the speed of light equals meters per second. Now, Newton only had these. But of course, in relativity, we've got an extra thing to play with. Einstein gives us this. Now, here's the killer. If I form the group gm over c squared, what units has that got? Meters cubed per second squared kilograms for g, kilograms for the mass, and meters squared per second squared. And lo and behold, everything cancels out except for a single length scale, which we've got here, which is meters. So the group gm over c squared has dimensions length. And we'll recognize this as the Schwarzschild, or half the Schwarzschild radius, later. But for the moment, I just want to observe that the Newtonian paradigm has got no standard length scale. There is no length scale built in to a point mass of mass m, whereas the relativistic view, dimensionally at least, has a length scale built into it. And what we're going to do is to investigate the physical significance of that length scale and see what it means and try and understand it. Okay? Okay, I guess it doesn't hurt to actually put some values in. Let's take a typical mass black hole. A black hole might have mass 10 times the mass of the Sun, which equals 10 times, the mass of the Sun is 2 times 10 to the 30 kilograms approximately. So I guess that's 2 times 10 to the 31. Big G is equal to 6.671 times 10 to the minus 11, and C of course is 3 times 10 to the 8, all in SI units. So our little grouping here, GM, well, I'll just work it out in R directly. I've got my R window here. See if I can, no, it's this one. There we go. Oops. Let's do that again. GM over C squared. So we've got 6.671 times 10 to the minus 11 times 10 times 2e30 for the mass of the whole over C squared, 3e8 squared. And this will be a length scale in meters, and it comes out to be 14,000 meters or 14 kilometers, which is quite small by astrophysical standards. Size of a sort of small moon, I guess. So it's a small size, but I want to investigate what it means in a physical context and in a mathematical context. And I'll spend dozens of screencasts talking about that. So I'm just going to stop there. No, I don't want to save. I'm going to stop there. Stop, 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 stop.